The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
Hi, morning everyone. My name is Yuan. I'm a PhD student from Northwestern University. My topic today is chemical admixture with carbon nanotubes. Conventionally, people are taking carbon nanotubes as a nanoscale fiber reinforcement for cementitious materials. We are taking this somewhat different approach and consider CNTs as a chemical admixture for cement materials. And I will explain why in my presentation. So this is my content of today's presentation. I will first introduce the background of my research and why we are interested in this topic. And then I will show you some effect of well-dispersed carbon nanotube in cement composite that we have seen in our lab. Next, I will talk about the processing of carbon nanotube suspension. The last will be the conclusion of this presentation. I will start from the background. So carbon nanotube is a tube-shaped graphitic carbon materials with extremely high Young's modulus and tensile strength. The Young's modulus could get up to 5 times larger than steel, and the tensile strength could get up to 50 times larger than steel. And the diameter of carbon nanotube ranges between 20 to 40 nanometer, and the length ranges from 100 nanometer to a couple micrometers. The aspect ratio of carbon nanotube is very high, can get up to 1,000, which makes the material very easy to agglomerate. Carbon nanofiber is another form of carbon nanotube. The diameter of carbon nanofiber is 50 to 150 nanometer, a little bit larger than CNT. And the morphology is also different from CNTs, which the graphite planes appear to cantate out from its longitudinal direction. So the carbon nanomaterial has excellent mechanical, electrical, and thermal properties, and it has been used in many composite materials. Even though it has the potential to improve the concrete materials on its low modulus, low tensile strength, and electrical property, it has never been used in concrete materials or construction industry. The challenges of using carbon nanotube or carbon nanofiber is believed to be its high cost and difficulties in dispersion, in separation, dispersion. We are managed to target both challenges by using only a small amount of addition, 0.08 to 0.15 weight% to cement. Then I will show you some effect of well-dispersed CNTs in cement composite. First, I will start from mechanical test with flexural test and compression test. The CNT is firstly added in cement paste, and the beams are tested under flexural test. We have seen 0.1% of CNF addition increase the Young's modulus from around 8 to 10 gigapascal at 28 days. The flexural strength increased from 5.4 to 6.1 megapascal at 28 days of age. Then the same dosage of CNF is added in mortar. The results show the modulus of elasticity is increased from 19 gigapascal to 26 gigapascal at 28 days of age, and the flexural strength is increased from 6.5 megapascal to 8.3 megapascal at 28 days of age. The concrete samples are tested with compression tests, and we found out 0.1 weight% of carbon nanofiber in the concrete cylinder is able to increase the modulus from 35.7 to 46 gigapascal, while the compressive strength is only changed from 47 to 50 megapascal. A table summarizes the results of mechanical test results. Though the dosage of CNF is the same in different cement mixtures, paste, mortar, and concrete, the volume fraction is different due to the different amount of cement in the mixture. And we found the increase in Young's modulus is not proportional to its volume fraction as the conventional microfiber does, which indicates a modification on the interface between the bulk paste and the aggregate. Also, the improvement on the Young's modulus, the significant improvement on the Young's modulus is particularly interesting for us, especially when there is not much improvement on the compressive strength. To investigate the interface between the bulk paste and the aggregate, we performed a SEM EDS test with concrete samples with or without the addition of CNF. The calcium to silica ratio is measured along the lines perpendicular to the aggregate surfaces. And the peak possibility of calcium to silica ratio for control sample is above 2.3, where is the region CSH combined with CH, while the peak possibility of our CNF sample falls between 1.2 to 2.3, where is the typical range of CSH. The results show the plant motor has a higher content of calcium hydroxide on the interface. With CNF added in the concrete sample, the results proves there is a chemical modification on the interface which distinguish the behavior of carbon nanotube and the conventional microfiber reinforcement. In addition, the improvement on Young's modulus, as I mentioned, is also impressive from the mechanical test. It is very difficult to improve the Young's modulus of concrete material. However, the modulus is a critical design factor, especially for high-rise buildings. An optimum goal of Young's modulus for a high-rise building is 58 gigapascal. To reach the higher requirement of Young's modulus, the concrete has to be stronger and stronger in terms of compressive strength. We all know Young's modulus equals 57,000 square root of F prime C. And to get to 58 gigapascal, the compressive strength needs to be increased to 180 megapascal, which is far beyond the design requirement of the compressive strength. As we know, with higher compressive strength, there will be higher cost, less sustainability in terms of construction. With carbon nanomaterials, as plotted in the left top corner in the figure, we are managed to get to 47 gigapascal for Young's modulus, but remain to be 50 megapascal in compressive strength. Approaching to the left corner of the figure, as I mentioned, means stiffer structure, cheaper, and more sustainability. Besides the mechanical properties, we have also tested other properties. With a small addition of carbon nanofiber, the alternate shrinkage is reduced by 25% at the end of 3 days. The shrinkage cracking test with mortar sample shows the CNF not only delays the formation of crack, also reduce the crack width by 30% at the end of 12 days. A half-cell potential test is performed to measure the resistance to the reinforcement corrosion. A steel rebar is embedded in smart mortar, and the half-cell potential is measured as an indication of corrosion activity probability. The steel in control sample is corroded around 20 days when the potential reaches 350 milliwatts, while the potential remains below 350 millivolts for motor samples with CNTs in 70 days, indicating no active corrosion for the steel rebar in the sample. The result proves CNT is able to increase the resistance to the corrosion. Next, I will talk about the processing of CNT suspension. As mentioned in the previous session, CNTs has high aspect ratios and thus extremely large surface area. It makes the nanomaterials tend to agglomerate due to the presence of attractive force. And the commercialized CNTs are usually supplied in the form of heavily bundled form, which results in challenges in dispersion. And the poor dispersion and rope-like entanglement of CNT in the composite matrix always leading to many defect size in the composite and limiting the efficiency of the use of CNT materials. A proper agitation must be used to break the CNT agglomeration. The picture here is showing a bad agglomeration, a bad dispersion in aqueous solution. Dispersion method could be characterized to chemical agitation and mechanical agitation. Chemical agitation is used to modify the surface properties of CNTs with chemicals, and the mechanical agitation introduce shear force to mechanically separate CNT agglomerations. They are often combined with each other with respect to the dispersion of CNTs. The chemical approach could be either covalent or non-covalent. What we are using in our lab is a non-covalent functionalization. This method is based on physical interactions, which the tube surface can be modified by absorptions or wrapping of surfactants, polymers, or biomolecules. A conventional shear mixing used for cement material couldn't provide enough shear energy to separate the CNT agglomerations. So several mechanical agitation were used in different studies to provide the large shear forces in order to mechanically separate CNTs from each other. The most used technique is ultrasonication energy. Dispersion through ultrasonication are the results of ultrasonic cavitation. The high intensity energy is passed through the medium and produce attenuated sound waves. These sound waves form ultrasonic cavitation in liquids, which causes high-speed liquid jets, and it applies mechanical stress on the attracting forces between the particles. High-intensity shear mixing, showing on the right, is an alternative option for large-scale dispersion with higher content CNTs. The final step of CNTs processing would be the evaluation of the dispersion effect. The commonly used method is ultraviolet visible spectroscopy. Individual multi-wall carbon nanotube is active in the UV-Vis region, and it shows a single peak between 200 to 1200 nanometer, as shown in the figure on the right. Contrary to dispersed CNTs, bundled form CNTs are not active within the wavelengths we measured. By taking a small amount of sample every hour during the sonication process, the absorbance is applauded as a method to demonstrate the dispersion dynamics. The peak values of each absorbance curve from the left is extracted and plotted with corresponding sonication energy as shown on the right. When the peak absorbance reaches its plateau, means the absorbance cannot be further developed and a fully dispersion is achieved. The dispersion method used in our lab at Northwestern is a combination of the use of superplasticizer, concrete-friendly water-reducing agent, and the ultrasonication tip. The complete process to work with CNT for cement material is to disperse the CNT powder, First, in the water containing a certain amount of superplasticizer, the sonication energy is delivered to the aqueous solution via ultrasonication tip at a specified amplitude. The total energy is then determined via a UVVS, the ultraviolet spectroscopy, and the CNT suspension is a well-dispersed CNT suspension is achieved, then added into the cement material without adding extra water. Now I will explain why we are taking CNT suspensions as a chemical admixture rather than a nanoscale fiber reinforcement. First, the dosage of CNTs is similar to chemical admixture rather than conventional microfiber reinforcement. So usually the microfiber reinforcement is at 1 to 5% weight percent, and our CNTs are at dosage of 0.08 to 0.15 weight percent to cement. Also, nano modification of the hydration products make it more similar to a chemical admixture rather than a fiber reinforcement. Last will be my conclusion of this presentation. First, CNTs can significantly improve the mechanical properties such as flexural strength and Yuan's modulus. Also, CNT can reduce outer shrinkage cracking. CNTs can increase the resistance to reinforcement corrosion, and a crucial factor to fully utilize the CNTs is dispersion, a good dispersion, and it has been already obtained in our lab scale. Our next step is to upscale the dispersion for industrial application. Thanks.
The question is, what's the impact on water demand when you add the material?
So for right now, we are using the water we need for the cement mixture to make our CNT suspension. So later, we will also try to improve the concentration of our CNT suspension, which will reduce the water demand of our suspension. So it takes several hours because the dispersion intensity cannot be too large because we don't want to break or damage the CNF or CNT. So to achieve the total energy, we have to disperse like for several hours. Yeah, even when we add the superplasticizer.
Yes, so the question is, what's the impact on slump, and is there a special requirement for the mixing of material?
We did measure the workability compared to the neat concrete, plain concrete. The workability is very comparable, like almost no change to the slump or the setting time. But the reason is we have superplasticizer inside our dispersion, so it helps the workability. Actually, we think the hypothesis the carbon nanotube or carbon fiber provide like helps the alignment of the crystal of the CSH, but so far there is no clear improvement on our hypothesis.
And you had a question here.
Do you have any specifications on the water?
No, just
Just tap water?
yes, just tap water. We cannot afford to use distilled water because it's a large application, and we later, like in the future, we wanna use that in the real like industry application. So we don't use like this distilled water. No specified on water.
Okay. Time for one more question. Any more questions? Right here.
Once you get the dispersion
We find it's very stable on the shelf. But right before we put it in the concrete mixture, we want to have a little bit re-disperse, like stirring right before we put them in the concrete. But just a small amount of stirring is fine. So it is like a very stable suspension on the shelf.
Okay, thank you.
Thank you.